Okay. Professor Bernstein is in DC today, and I agreed to finish it for him. He wanted me just to show a few slides having to do with fusion reactions. I think he's familiarized you with fission, and particularly what is useful for fission power reactor weapons is the fact that there are some actinides where you just drift in thermal neutron is fractured, and bang, you get with order unity probability a fissioning event plus more neutrons, which can then lead to a chain reaction. We're going to talk today about fusion, and I've been asked to be brief and just to show a few slides. What's interesting is when you look at the history of, this is we'll show a few graphs on this. If you look at the history of fission power, fission was discovered as a scientific by Hahn and Strassmann in December of 1938 by all of a sudden, by December of 1942, Fermi had created a reactor, University of Chicago, graphite moderated reactor. By 1945, you had nuclear weapons. You had, by 1950-51, you had a 100 kilowatt reactor made by our national lab. Fission, or it was like falling off a log. In the case of fusion, Blackett, and I'm trying to remember who else actually sort of filed a patent in 1946 on the fusion of very light elements, which produce per nucleon much more energy, a lot of energy. And yet, by the time we get energy on the grid, one can confidently say a little bit more than a century. You say, why was one like falling off a log and the other was like, you know, a moonshot? Why is fusion so more difficult than fission? And we'll talk to that. And it basically has to do with, whereas in the case of a fission reaction, a thermal neutron drifting in has a very high cross section. The neutron absorbs, bang. In the case of fusion, you require things to be very dense and very, very hot. Now, here's the interesting thing. When you look at the case of fission, which I believe you've done before, what's the average energy of a fissioning event, very grossly? 200 MeV. How many nucleons are taking part in this whole act? Yeah, so what's the average energy released per participating nucleon? Less than 1. Here you have a situation, if I take the best fusion reaction, deuterium plus tritium, going to a neutron plus an alpha particle, where it's releasing close to 18 MeV over where there's 5 participants. So there's more than 3 MeV per nucleon involved in this reaction. What's not to love? Okay. Now, the problem is, the difference is that in the case of a neutron in uranium, a thermal neutron can just drift in like this because it's uncharged and there's no Coulomb repulsion. In the case of deuterium and tritium, they are both charged. They're both charged in 1. But that, even so, the electrostatic repulsion keeps them at a distance where the nuclear force, unless you get them moving fast enough that the nuclear force is effective, generally the nuclear reaction won't go. That's the issue. There, he's made a little bit of a mistake here. He's drawn diameters, but he's correctly stated radii. These little objects are deuterium is a couple of. Deuterium is a very loosely bound nucleus. It's actually large and floppy. The neutron and proton larger than the distance that you would calculate by the usual A to the -1/3 law. But it's a couple of Fermis. Tritium is a couple of Fermis. And when you calculate the Coulomb barrier, it turns out to be on the order of a few hundred keV. Now, we'll get to that in just a second. But here are the cross sections that are involved in three very common fusion reactions. If some of you, I think many of you have probably taken a tour or actually participated in experiments that we do down at High Flux Neutron Generator in the basement of Etcheverry. That's a DD, deuterium-based, and there's the cross-section where the fusion of two deuterium nuclei to make a neutron plus a helium-3. And at the energies we're using down at the high flux neutron generator, about 100 kilovolt energy, the cross-section you see is on the order of some 20 or 30 millibars. DT goes like gangbusters, and the reason for that is the extremely tight binding energy of the alpha particle. There you're up to 10 bars. So this is a terrifically large, a very usable cross-section there with a lot of energy release, close to 18 MeV compared to about 2.5 MeV right here. Now, people who are designing reactors, magnetic fusion reactors, or inertial fusion reactors, like NIF, are trying to get things dense enough and hot enough to produce a plasma of typical temperature on the order of some tens of keV. Question is, and you can see there are, the cross sections are quite reasonable, but you're not anywhere near the peak. It turns out that's usable enough. And this gets into the issue of quantum mechanical tunneling. If I calculate the classical, if I take two spherical objects of charge like this, and I make them touch at their mutual radius, so I have R1 and R2, and calculate, and this one has Z1 E charge, and this one has Z2 E charge. You can calculate the energy required to make these two things kiss, just like that, to bring them touching. This is not a bad approximation to the nuclear force, because to get nuclear reactions to go, they have to be close to touching or darn near touching. Lee and I debate whether he says, well, the nuclear force is really effective at 5 or 6 Fermis, but they really go like gangbusters once you get them within 1 or 2 Fermis, about the diameter of the nucleon itself. And you can do this calculation. The Coulomb barrier, some people here will not see it, so what I'll do is put it up here and then boost the thing up. Is in standard units, it's nuclear physics units, it's E squared, or Z1, Z2, E squared over the radius of separation between the two. And in units which are convenient in nuclear physics, so this would be Z1, Z2. In the case we're talking about now, both Z1 and Z2 are 1. This is 1.44 MeV Fermis. And down here, just say 2 Fermis for one, 2 Fermis for the other, 4, like that. You come up with numbers on the order of 300 and something keV. So you say, why, when people design a fusion, magnetic fusion reactor, or they're compressing things at NIF, why are energies or temperatures on the order, which is an average energy, on the order of a few keV or so, a few tens of keV sufficient? And this comes to the fact, because classically there, you've not got the nuclei anywhere close enough, you would imagine, for the nuclear force to do its thing. This gets into a very mysterious and very beautiful topic in quantum mechanics, and we do not want to digress here, having to do with tunneling. In the classical world, if you want to get a boulder over a hill, you've got to put the energy, you've got to ultimately put enough energy in such that at some point in the trajectory, you've supplied the energy associated with the top of the hill, mgh. Quantum mechanics is very different. In quantum mechanics, something which is not allowed classically, so there is a potential energy, if I'm talking about a gravitational problem here, the hill represents, in fact, that curve represents the curve of potential energy, mgh, mass, the acceleration of gravity at their surface, and then h is the height. There is a small probability that if I throw a rock at a hill, it will appear on the other side. Of course, in the classical world, the macroscopic world, the probability for that to happen is really zero. In the subatomic world, that happens from time to time, very, very rarely. Professor Bernstein, I think, just talked about alpha decay. Okay, that's an example of tunneling that happens when an alpha particle actually pops out of a nucleus, but there is a Coulomb barrier actually keeping it in. The alpha particle is kind of bouncing back and forth some very large number of times a second, and then once every, depending on the nucleus, what the final energy is, what the Z of the nucleus is, and this could be on the order of many billions of years, all of a sudden, on the average, the alpha particle all of a sudden boop, pops out quite magically and is on its way. It sails down the Coulomb barrier. It's got 5 MeV of energy at the end. This is a very nice, we're going to put this up on eCourse, a very nice video. It's about a 6-minute video. We did not want to hold things up since Professor Nam has a somewhat lengthier lecture here today. But this gives you a little bit of an interesting insight into the weirdness of the quantum world. And so here is the interesting paradox. When you look at fission, if you look at, for example, power reactors and fission bombs, you actually find a cross-section, probability high for, cross-section is the thing which encodes the probability of a neutron being absorbed or a reaction taking place, gets better and better and better as the velocity or the energy of the neutron goes down. Here, in the case of charged particle reaction, due to the Coulomb barrier, these things are plummeting like a brick as you go down in energy. So thermonuclear reactions work best at high temperatures, and fission reactors work best at low temperature. And then bringing this back to the subject at hand, if you look at nuclear weapons, and I think Lee has talked to you a little bit in general terms about a modern boosted two-stage weapon having a primary high explosive driven stage to get a fission reaction, one-way reaction going, a chain reaction going that produces an immense amount of energy and X-rays, which are then channeled and focused on the secondary, such that you can get a tremendous compression there. The primary works on the principle of fission. The secondary works largely on the issue on the principle of fusion energy release. Although the fast neutrons coming out of here, this thing is designed to pelt usually a large tamper of uranium, such that you also get a lot of additional fission energy out as well. Okay, this slide here, if you translate these energies on the order of tens of kilovolts into degrees Kelvin, it actually turns out to be a very large number. And I'm trying to remember the number. So when KT in physics units or atomic units is 1 eV, that actually corresponds to, I'm trying to remember this, but I'm sure some of you remember this better than 11,600 degrees Kelvin. So if I want 10 keV, you're now talking about things that will be on the order of, for example, 100 million degrees Kelvin. I think with that, I'm going to stop. Take questions, and then there's be a little transition for Professor Knox lecture today. Any questions about fusion? Check out that web link there on tunneling. It's, I think, quite interesting. I did not want to slow down their class since there's a lot to do today. Okay.
Marissa, if you want to make your announcements.
Yeah, so I sent out an email that we're going to be having our class meeting on Wednesday at 1. It's going to be in 3105 Estuary. I'll send out another email reminding you of the room. So make sure you meet with your small groups and choose a representative to present to the rest of the class. And if you can't make it, it's not a big deal. We're going to be taking notes, and so you can kind of contribute remotely. But make sure at least one person from your group is there to represent.
Okay. Thank you, Carl. Okay. Well, okay, well, remember me. I got you to atomic bombs at the end of World War II, and then sort of I've played a more cameo role since. So now we're going to have a very extensive and somewhat intensive examination of the evolution of U.S. nuclear thinking, nuclear strategy in the 50s and 60s, which really set the groundwork for current thinking about nuclear weapons. And some of this may be familiar to some of you, I'm not sure, but I'm going to go through each of these points and a few others that are not on the list. One of the initial questions that came out after the war, so again, to summarize, of course, after the war, the U.S. had used the only nuclear weapons ever used in anger. Hiroshima and Nagasaki, both alternate targets, were hit. Several 100,000 people were killed. There were moral, tactical, political, strategic, military issues involved in the Truman decisions, but nonetheless, those were decisions. And then almost immediately after the war came this intense competition with the Soviet Union, which became the Cold War. There was hardly any gap between the end of World War II and the start of the Cold War, maybe about 18 months. So the U.S. is sitting on a stockpile of nuclear weapons. Oppenheimer, the Berkeley physicist who ran the Manhattan Project, was still at Los Alamos. And an initial question that arose almost immediately was, who controls these weapons? Who on the U.S. side? This is a U.S.-focused presentation. Who controls these weapons? You know, if you ask about howitzer shells, the Army controls howitzer shells. If they're aircraft, after the National Security Act of '47 created the U.S. Air Force, the Air Force controls aircraft. If you look at submarines and aircraft carriers, the Navy controls. Right? The military services control their main tools for waging war. But where did nuclear weapons fit in? Not so obvious. And after considerable discussion and debate, it was determined that these were so lethal, their uses could be so catastrophic that none of the services should have control of the nuclear weapons. They should be controlled by civilians. Going back to the American tradition of civilian control of the military. So an organization was established, the AEC, the Atomic Energy Commission, established in '46, and it had a bunch of senior people from Wall Street and politics and other people, some scientists sitting on it, and they were like the board of directors for control of the kinds of weapons to be built, the types of weapons, where they would be deployed, and possible ideas for their use. And just sticking along this line, the AEC was replaced in the mid-'70s as Nixon was fading out because of Watergate and Ford came in. ERDA was formed, the Energy Research and Development Administration. It had a broader perspective than the AEC because we had developed several major weapons laboratories, particularly Los Alamos, of course, from the Manhattan Project, then Livermore, which I'll tell you about in a minute, and Sandia. And there were many other nuclear energy related issues related to peaceful uses of nuclear energy. So ERDA had a broader perspective on nuclear energy than did the AEC. And they lasted only a short time, and then when Carter became president in '77, he proposed and the Congress approved the establishment of the Department of Energy, DOE, which is the current governmental organization that controls nuclear weapons today. The secretary, the cabinet secretary of DOE is, you know, Secretary Rick Perry, former governor of Texas, not a nuclear scientist. The previous one was Ernie Moniz, a nuclear engineer from MIT. He wasn't a nuclear scientist, he's a nuclear scientist. So this has been at the top how the weapons have been sort of orchestrated. But there are many, many other sub-issues of great importance. One is, who builds the weapons? Los Alamos built the weapons, basically took the weapons from Oak Ridge and from Hanford, which we discussed previously, and they were designing and developing the specs for future nuclear weapons in the 1940s after the war. There arose a major dispute, this is number 3 here, between two of the giants of the time, Oppenheimer, the Berkeley physics professor who was head of the Manhattan Project, and Edward Teller, who was a subordinate to Oppenheimer on the Manhattan Project. And Teller had the strongest views that thermonuclear weapons were the wave of the future, not fission weapons. What you heard from Professor Bernstein and Professor De Bibber feeds directly into this point. You see that the magnitude of energy released by a thermonuclear weapon dwarfs that of a fission weapon. Teller was a Hungarian refugee, a Jew, deeply anti-Russian and anti-Soviet, who said, if we know how to build these weapons, then the Soviets will know how to build it. We must be in the lead on thermonuclear weapons. Oppenheimer, American-born, German ancestry originally, Jewish, but very profoundly moved by seeing the destructiveness of Hiroshima and Nagasaki, said, it's crazy to continue to build more and more destructive nuclear weapons. And he took an opposing view to Teller on whether thermonuclear weapons should be designed, built, and deployed. The key experimental scientist here
Ernest Lawrence, who had built the cyclotron, sided not with his Berkeley colleague, but with Teller. And because the military was interested in more bang for the buck, so they wanted thermonuclear weapons. And at that time, the key chairman of the Atomic Energy Commission, a man named Lewis Strauss, S-T-R-A-U-S-S. This is discussed in Kaplan. Strauss also sided with Teller on the need to develop thermonuclear weapons. Now, there was a separate angle about Oppenheimer's background. Oppenheimer had left-wing politics. His wife had been a member of the American Communist Party. His brother had been a member of the American Communist Party. His brother, Frank Oppenheimer, have any of you heard of the Exploratorium in San Francisco? Frank Oppenheimer designed and built the Exploratorium. He had been denied a clearance to work on the Manhattan Project because of his Communist Party affiliation. This is right out of Greek drama. So Teller, in advocating for thermonuclear weapons, said that maybe a reason Oppenheimer is not advocating for it is because he's got Soviet sympathies. This is hardball. This is about, as Trump said about Doug Porter. Doug Porter? Rob Porter, yeah. It's career busting. Right? Teller is aiming to bust Oppenheimer's career with that kind of innuendo. It's hugely significant. This is massive. This is when people read newspapers, front page articles, gigantic banner headlines like this. So the Congress, which had many conservative members, decided to hold hearings, Oppenheimer-Teller hearings, not only about the feasibility and desirability of thermonuclear weapons, but whether Oppenheimer himself should continue to hold security clearances. He was the man who had, was the orchestrator of the Manhattan Project. And there never had been any direct connection between Oppenheimer and any communist organization. Yes.
Was this before or after 1949, the hearings?
53, 54. So one point in the hearing, there's a very dramatic moment when one of the senators asked Teller whether he thought Oppenheimer was trustworthy enough to continue to hold the highest security clearances. And he gave a very waffled, mediocre, squishy answer, not a yes. And that was taken as evidence by the conservatives on the Senate that they should remove Oppenheimer's security clearance. And they did. And this shattered Oppenheimer, because without the security clearance, you can't be involved in all of the classified discussions on weapons development, which was the heart of what Oppenheimer was doing. Oppenheimer later left Los Alamos. He became head of the Institute for Advanced Study at Princeton, a premier think tank where Einstein was in residence and other very famous natural and social scientists. And he spent the balance of his career at the Institute for Advanced Study. He wrote, he commented, but he was not involved in the national security debates that required security clearances. He was an enormous smoker of cigarettes at a time before it was fully understood the cancerous impact of cigarette smoking. And in fact, any photo you can find of Oppenheimer doesn't have him smoking a cigarette. And he died of lung cancer in his 60s, in the 1960s. In the meantime, not only did Teller prevail over Oppenheimer on the desirability of building thermonuclear weapons, but he insisted that because Oppenheimer was a godlike figure at Los Alamos, that Los Alamos itself should not be the organization design and build thermonuclear weapons, that there should be another laboratory, a competitive laboratory to build them. And that became the Lawrence Livermore National Laboratory, which is 40 miles from here, right out 580. And they became a second nuclear weapons design laboratory. In addition, during the war and with the Manhattan Project, you know, it turns out that nuclear weapons are 95% non-nuclear materials. It's about the metal casting, it's about the fusing, it's about all kinds of technologies that have to work properly together, but not nuclear. So there's a whole gigantic engineering dimension to nuclear weapons development that's not nuclear physics. And that was being done by a chunk of folks at Los Alamos, which was decided after the war should be split off as a separate engineering laboratory. And that became known as the Sandia National Laboratory. Sandia is headquartered at Kirtland Air Force Base in Albuquerque, New Mexico. And they have a second, smaller satellite facility across the road from Lawrence Livermore National Laboratory right here in Livermore. If you go out to Livermore, you've got the huge Lawrence Livermore Lab, which has about 8,000 employees. And you've got the small Sandia satellite facility, which has about 1,000 employees. The other, Sandia has about 10,000 other employees at Kirtland in New Mexico. And in the meantime, Los Alamos is still doing their thing in Los Alamos in northern New Mexico. So those are the three nuclear weapons laboratories, two weapons design labs, Los Alamos and Livermore, and one engineering lab, Sandia, who works with both Los Alamos and Livermore. Is that clear? How many of you have familiarity with that, Los Alamos, Livermore, Sandia? Should it very close connection between the nuclear engineering department and these laboratories. Okay. Now, this is all about the scientists arguing with themselves over turf and design and organization, this and that. But they're not going to be the ones who are going to use the thing. It's going to be the military who still use them. So after the 1947 National Security Act, which created the Air Force, this was going to be the Air Force's key mission. They were going to use nuclear weapons, and they were going to base them on different kinds of delivery vehicles, which gets us down here. Over time, the U.S., with a lot of internal debates, none of this was magical, this wasn't preordained, this was the consequence of a lot of internal struggles between the services, within the services, between the services and the weapons labs, with members of Congress, with industry. You know, the U.S. never does anything simple. It's a complicated, difficult struggle. The U.S. did develop the Triad, T-R-I-A-D, which means a three-way capability to deliver nuclear weapons. One way are intercontinental ballistic missiles. These are ground-based missiles. They're headquartered they're housed in underground silos in the Rocky Mountain states and the Northwest. And the Soviets built large numbers of these as well, ICBMs. The Navy wanted to get into the nuclear business, and they had a very talented naval engineer, Hyman Rickover, who pushed forward the Navy role in the nuclear business. Not only submarines that were propelled by nuclear reactors, but submarines that could carry ballistic missiles with nuclear weapons. The submarines that are using nuclear reactors but don't carry missiles are SSNs. You need to know all this. All this is required information for you, so I hope you're taking it down. SSNs are subsurface nuclear missiles. Those submarines that carry ballistic missiles are SSBNs, subsurface ballistic nuclear. And subsurface ballistic nuclear submarines carry submarine-launched ballistic missiles. So the SSBNs carry SLBMs. That's the second component of the triad. The first are the ICBMs. The second are the SSBNs that carry the SLBMs, not to be confused with the SSNs. It's very interesting that in the new nuclear posture review just released, for the very first time, the Trump administration is advocating that SSNs would carry nuclear weapons. This is a revolutionary development, should it be carried forward. And the third element of the triad, besides ICBMs and SSBNs, are long-range bombers, strategic bombers, or heavy bombers. These are bombers that can fly intercontinental ranges. We've had, for over 50 years, the B-52s, which have been designed and redesigned and upgraded many, many, many times. We also have the B-1 bomber and the B-2 bomber. They are stealth bombers. Stealth technology is special coating on the frame of the aircraft so that they cannot be detected by radar. The B-1 bombers do not currently have a nuclear mission. The B-2 bombers do have a nuclear mission. Do you have a question?
I was going to say that the B-1Bs were denuclearized some years ago and have had modifications made that they cannot be easily made.
Right, that's right. The B-1B is sort of out of the nuclear mission. The B-2 is not. The B-2 is a nuclear mission. And this has even come up in the crisis over North Korea, if you've been following it. When the North Koreans were testing missiles and threatening to attack Guam, Guam has B-52s and B-2s on the island. So it's not casual that North Korea would be thinking of targeting Guam. Now the ballistic missile, whether it's sea-based or where can I be seen, Sarah? Where can I be seen, over here?
Yeah, wherever.
The ballistic missile is a multi-stage system which ultimately throws a re-entry vehicle, pardon my terrible autistic ability here, into a parabolic orbit, parabolic trajectory. And it is the re-entry vehicle, which has warheads in it, that goes to the target. The early stages of the missile do not. So this is, it's gravitational force. You understand, you can determine aerodynamically what the trajectory would be of the re-entry vehicle in order to hit the target. So separately from this, and this is ICBMs and SLBMs, separately from this are cruise missiles. Cruise missiles are not gravitationally propelled. Cruise missiles are fueled in flight and they usually are very low altitude, just a few hundred feet. Whereas the ICBM could be 100 miles up. The cruise missile carries a propelled re-entry vehicle, a warhead right to its target. And the advantage of the cruise missile, it's slow, that's not an advantage. It's low altitude, that's not an advantage, but it's hyper accurate. There used to be a system for guidance for the cruise missile called TERCOM, terrain contour matching. This is not in the book. Terrain contour matching is that there's an onboard computer for the guidance system of the cruise missile. and the cruise missile would have in it digitized the terrain of its entire trajectory from launch to impact. So 1 second. And it constantly is looking at where it is in comparison as to where it should be and making changes. So it comes right down the hatch. So for example, the Russians have cruise missiles on board ships off the coast of California. And if they wanted to say, let's hit the new Goldman School building and not the old Goldman School building, they would have the accuracy to do that. It's precision targeting. This is not, the ICBM and SLBM does not have that kind of targeting. It's improved a lot, but it's not nearly as good as a cruise missile. There was a yes.
So why would you use a cruise missile if it's slow and you're launching a nuke anyways?
So there's a question there. It might be because you want precision attack. It might be that you want to surprise the adversary, because the cruise missile could be based on submarines or surface ships. It could mean that you could convince yourself that if it's not coming from the continental United States, it's not a strategic weapon, and therefore shouldn't necessitate a response to the U.S. homeland. Yes.
And then which ships? So we know the submarines and the SSBMs carry SLBM. But which ships could carry the cruise missile then?
So there are, there's been change in that over the years. There are carrier-based aircraft that carry cruise missiles, and there are heavy bombers that carry air-launched cruise missiles. The cruise missile has, used to have 3 types of flavors. There's 2. There used to be something called a ground-launched cruise missile, or Glickum, a sea-launched cruise missile, or Slickum, an air-launched cruise missile, or Halcum. These and these still exist. This does not exist in the U.S. arsenal. So this is what you're hearing from me now is a reflection of inter-service rivalry, of diversifying means of attack for military purposes, of trying to add logic, if that's the right word, to the whole nuclear issue. Oh, I see I did have here, Alchem, Glickum, and Slickum. Alchem, Glickum, and Slickum. In the early 1980s, there was tremendous Soviet military force in Eastern Europe. Every one of the countries of the Warsaw Pact, Poland, Hungary, the Czech Republic, and even Romania and Bulgaria and East Germany in particular had huge numbers of Russian Soviet ground forces. And these also had, there were nuclear weapons deployed in Central and Eastern Europe. And at one point in the early 80s, when Reagan was president, the Soviets deployed the SS-20, which was a medium-range ICBM. It's shorter range than the ICBM, but that could target all major military targets and cities in Western Europe. It was viewed as extremely dangerous and destabilizing development. These were Soviet SS-20 deployments in Eastern Europe in the 1980s. And Reagan, after lots of discussion and despite opposition from many Europeans who didn't want the U.S. to respond, deployed Pershing 2 missiles. These are also medium-range ballistic missiles. They're intermediate-range ballistic missiles. And Glickums to counter the SS-20s. Yes, there was.
If the Russians, or like the Soviets and Americans had intercontinental ballistic missiles that could hit like any target in the respective countries anyway. Why does it matter if they also had intermediate range missiles?
Great. So why does it matter? Because this questions whether if I've got a capability to destroy your homeland and you've got a capability to destroy my homeland, it may be that we nullify each other. That's mutual deterrence, or actually it's called mutual assured destruction. But it doesn't mean that ends our appetite for aggression. We may want to attack allies or threaten to attack allies and achieve dominance over them. So the concern was that the Soviet deployments were intended to coerce the West European countries into adhering to Soviet preferences rather than to stick with the Americans.
Gotcha. So why was the Cuban Missile Crisis such a big deal?
Why was the Cuban Missile Crisis such a big deal? Okay, I can talk about the Cuban Missile. I was alive during the Cuban Missile Crisis. It's a conjecture, but I think I'm still alive now. So it's we debate that. I'm going to tell you something about the Cuban Missile Crisis. The Cuban Missile Crisis was, in a way, a connection to this. Khrushchev ordered missiles deployed on Cuba 90 miles off the Florida coast that could attack a range of targets from New York and Washington down the coast, as well as Norfolk, a huge naval base, and so forth. Now, the U.S. had already deployed some similar systems in Turkey, not far from the Soviet territory. We thought that was okay. We didn't think this was okay. We also were very concerned because we didn't know about Castro's stability and whether the Soviets gave him authority to use these weapons. This was done in a very secretive time. It's hard to imagine because of all the leaks now on social media whether this could have been carried out again. This was in October 1962. I'm going to introduce myself into the picture, although I was not a key player in the Cuban Missile Crisis. I was an engineering student, and on a Monday night, it was announced that President Kennedy was the U.S. president, Kennedy was going to make a televised address of monumental importance to the nation. This is non-trivial. To use that kind of language, it means get your attention. And he said that the Soviets had put these missiles in Cuba. They were threatening targets in 1/3 of the U.S. This was intolerable for the United States. We wanted all the missiles out of Cuba. The missiles were transferred from the Soviet Union to Cuba by sea, and he announced not an embargo. An embargo is an act of war in international law, but a quarantine. Quarantine is not an act of war. It's the same thing. Which meant we would have ships that would intercept Soviet ships bringing new missiles to Cuba. And Kennedy said, if any missiles from Cuba attacked any targets in the Western Hemisphere, so if they had a missile in Cuba that attacked Guatemala, then the U.S. would consider this an attack by the Soviet Union on the United States, requiring a full retaliatory strike by the United States on the Soviet Union. I don't know if you get the significance of that language, but it's a hyper threat. Going back to little old Michael, I was in engineering class and I had an exam scheduled the Thursday after the Kennedy speech on Monday. And we came into class on Tuesday, and the professor said, we have this gentleman, I think there was one engineering performance student in the rooms, old times. Gentlemen, he said, we have an exam scheduled on Thursday, but I'm not going to give out the exam on Thursday because I do not believe I will be alive to grade it. Think that got my attention at the age of 18? Not got my attention. The Soviet ships aimed toward the blockade, toward the quarantine, but ultimately did not challenge it. And there were no attacks, no use of Soviet missiles from Cuba anywhere. In the meantime, there's a lot of diplomacy on the side. And then the U.S. actually concealed the bargain that was struck. The actual bargain that was struck was, the U.S. had already tried to overthrow Castro. They had been the Bay of Pigs. I don't know if you're familiar with any of this. The U.S. vowed not to seek the overthrow of Castro in the future, and also vowed, with a decent interval of time, to withdraw U.S. intermediate missiles from Turkey that were close to the Soviet Union, in return for the withdrawal of all Soviet missiles from Cuba. You get that? But this was the ability of the U.S. to refrain from going after Castro and the withdrawal of the missiles from Turkey were not announced at that time. And it appeared as though Khrushchev was the head of the Soviet Union. He had backed down, and Kennedy had sort of won the eyeball to eyeball conflict. Dean Rusk, who was the Secretary of State at the time, said we were eyeball to eyeball, and the Soviets blinked. So Kennedy, it was interpreted in the world press, prevailed in this crisis. This is considered the closest we've come to a nuclear exchange with the Soviet Union since, at any point in the nuclear age. Does that sort of answer part of the question? Again, you have to understand, great powers are involved in an infinite chess game. This is the history of international politics. Seeking advantage, seeking to constrain the other party, seeking to gain allies over the other side. And this is what was happening during the Cold War. Now, slowly but surely we're covering some more of this stuff. There was another critical conceptual breakthrough in the early 50s coming out of RAND. I think I told you that RAND was a think tank. One of its origins was Donald Douglas, the head of Douglas Aircraft Company, who built major aircraft. And RAND became a think tank to study nuclear war. Even its existence was classified in the 1950s. There was no open knowledge that RAND existed. It was in headquarters in a building in Santa Monica, right near the Santa Monica Pier, if you know where that is. It now has a big facility in Washington, across from the Pentagon. It has a facility that does domestic analysis of policy in Pittsburgh. It also has had offices in Brussels and elsewhere. But its fame has been nuclear strategy during the Cold War. During the Cold War, there was a question, what do we do with our aircraft? Remember, in the 50s, we only had aircraft that could carry these weapons. We didn't have ICBMs yet, we didn't have SLBMs yet. They didn't come until the 60s. And it was decided by the Air Force, let's put the aircraft on the coasts to get as close to the Soviet Union as possible. And there were aircraft based up and down the West Coast, Vandenberg Air Force Base, and elsewhere, that would be headed toward the Soviet Union in the event of war with the Soviet Union. A small group of RAND analysts, led by a man named Albert Wohlstetter, was a very controversial character, who I later tangled with in my own career. He was a philosophy major at Columbia, who dropped out of his PhD program because he said his thesis advisor didn't know enough to advise him. He was hugely arrogant guy, but very, very smart. And Wohlstetter led a group at RAND to say, to put the US aircraft on the coasts is exactly the worst possible place to deploy them, because it makes them most vulnerable to attack. He said, the key element, remember this is after Dulles had talked about massive retaliation, and Brody had said that this was not credible. This is all in the Kaplan book. The Wohlstetter team said the core element for nuclear stability is secure retaliatory capability. You have to convince the adversary that no matter what he or she does to you, you have the ability to retaliate with such massive force as to destroy them. That's the only way to convince them not to attack you. This may seem very simple, not complicated, but it was a revolutionary idea at the time. Secure retaliatory capability. And that ultimately became absorbed by the military and is still a central feature of US targeting and basing policy to this day. Questions or comments at this time? How many of you are very familiar with all this? This is all old hat to most. You could leave. This is in Kaplan, but it's not all in Kaplan. So I'm embellishing and giving you a lot of addition.
Question.
Yes.
So his change from instead of having them based on the coast, what did he think instead?
So instead he said, rebase them inland so that the Soviet bombers have to fly a long distance in the United States to get to them in Kansas City, in South Dakota, in Missouri, which is where they're based today. So it's a redeployment from the coast to deep inland. Good point. Sorry, I omitted that. Yes.
So to follow on that, what didn't that also, the only reason they were able to do that was because of there was a colonel down in Florida who, through an accident, had developed a plan to be able to refuel the bombers so that we could fly from the US and still be able to hit targets without having.
Yeah, refueling is that's of course hugely significant. That didn't exist magically either. You know, you can't just get in an airplane and say, I'm going to fly 7,000 miles now. So you had to have a refueling capability, which we had more advanced one than the Soviets. There's also questions about air defense and missile defense, which I'm not getting into here, but that's another key element of this. Yes?
Can the ICBMs you were describing earlier not hit the target anywhere in the world? Do they have a range on it?
No, basically they can hit any target.
So again, why do we need bombers?
Great question. So, and this has been a debate that's gone on. Actually, the new Nuclear Posture Review just published last week. You can get online. Addresses this question. So if you have ICBMs that can hit any target, why do you need slower, maybe more vulnerable bombers? What would be the rationale? Yes.
You can't recall a missile once you've fired it.
Great. Recallability. You know, you might have second thoughts. You know, maybe I don't want to blow them up. I thought about it. Maybe it's not such a good idea. The bomber, if there's a man in the loop, or a woman in the loop, there are women pilots now at the B-52s. They're recallable. Yes, what else?
See, posturing essentially, we use the missile fields as the last strike, but you can't put a B-52 you can put a B-52 Spirit immediately proximate to your adversary or even over them in some cases. And that has more visceral effect in your strategic messaging and your planning there. See, third options. Honestly, they're cheaper than a single missile. You fire one missile, we don't really have the way to bring that back as easily as rebuilding. Suppose just say it's probably cheaper per unit.
Okay, another aspect I'd say is the bomber can not only be recalled, but can be shifted to a different target. The missile cannot. Once it's programmed to hit target X, it's going to hit target X. So again, the bomber is seen as providing added flexibility to the triad. In the meantime, what's happened though, and the debate was all about this ICBM versus bombers for years, but it's the SLBMs on the SSBMs that have achieved much greater prominence in the last 30 years. Why is that? Somebody else. Why are they more prominent now? Yes, sir.
Because they could be launched at any point that the submarine could be at the world.
Yes, and the inference of that is that they're the least vulnerable to attack. The SSBM is in thousands of square miles of ocean area, and at least until current times, they've not been able to be located. Now we're moving into a brand new world, a space-based world, a laser-based world. Your world will be very different from my world. And if the SSBN is locatable, and the SLBMs can be destroyed by a bombardment attack of various kinds, that can change the whole calculus of nuclear strategy. So for the last 40 years, the SSBN has been seen as the least vulnerable element of the triad. Okay. Other questions or comments about this? Otherwise, I want to get into this phase here. This gets back to some of your earlier reports. You know, I think I mentioned when we first talked about development of atomic physics, Kuhn talking about the paradigm and it shifts and it keeps evolving. And all the work you hear from Professor Bernstein and Professor Van Bibber explains our current understanding of atomic physics, of nuclear physics, which is based on many, many years of research. Well, in its own simple way, the same is true as here. The same is true here. Nuclear strategy is evolving. People are thinking through, maybe this doesn't work, maybe this is not credible to Soviet planners. How much do we know about how much they think about this? I'd say under Eisenhower, in the 50s, the thinking was relatively primitive. The folks there were from industry and from the military, not that they're not sophisticated people, but they really didn't pay a lot of attention to the sort of cerebral work of nuclear strategists. This changed when Kennedy came in. Kennedy chose a wunderkind from industry, Robert McNamara, a native of Oakland, California, a graduate of UC Berkeley, and then a graduate of the Harvard Business School, who had become the CEO of the Ford Motor Company in his 30s. And Kennedy asked him to become Secretary of Defense. It's an amazing appointment. But McNamara, unlike the Eisenhower folks, had ties to RAND, had ties to the intelligentsia, ties to the people in the book you were reading about with Kaplan. And one of them was Bill Kaufman. Bill Kaufman was part of the RAND group, part of the Deterrence group. He had been at Princeton, he had been at Yale, in the Institute of International Studies. He had written his seminal paper, The Requirements for Deterrence, which talks about credibility, which is will and capability. And McNamara asked Kaufman to be on his side and to think through Kaufman's efforts at nuclear strategy. Now, McNamara got sidetracked in major ways with Vietnam and led to, catastrophic results, and he ultimately had to resign. But he was the shaper of contemporary U.S. nuclear strategy. McNamara with Kaufman at his elbow. Kaufman, we talked about at a faculty department at MIT. I knew him in the last 30 years of his life. He's an amazing figure, a trenchant thinker, and his writings were incorporated into the defense posture statement of every Secretary of Defense from McNamara in '61 through Harold Brown in 1980. So for 20 years, the official U.S. document on military strategy, including nuclear strategy, was written by Kaufman. This has not happened since. Kaufman spoke and wrote endlessly about the credibility of the deterrence threat, about the shift from massive retaliation to flexible response. Even with these horrific weapons, we needed flexibility. Flexibility in what kind of weapon we would use, how vulnerable our own systems would be, what kind of targets to hit. They developed distinctions between three kinds of targets. Counter force targets, hitting the other guy's weapons. Counter value targets, hitting the other person's cities. And counter industrial targets, hitting the infrastructure. Think of Pearl Harbor. What was Pearl Harbor? If you had to assign one of these to Pearl Harbor, what kind of an attack is Pearl Harbor by the Japanese? Yes. It's a counter force attack. The Japanese have carrier-based aircraft. Are they going after the hula skirts in Honolulu? No. They're going after the ships that had aircraft that could attack the Japanese homeland. You're trying to destroy the military capability of the other side. And increasingly over time, counter-force capability ascended in importance in nuclear targeting, much more so than counter-city targeting. This was no longer about just busting up cities and having many, many examples of Hiroshima and Nagasaki. The U.S. realized it couldn't get into a game like that. We destroy Moscow when they destroy Washington. There's no winner in that game. So they actually use the term, it's not here, assured destruction. McNamara was asked, what kind of capability do we need to have to deter the Russians? And he said, we have to be able to assure ourselves and assure the Russians that a chunk of their population, and he had different numbers, 30, 40%, and their military capability, 40, 50%, could be destroyed. But over time, the Russians had the same capability to do that to us. So this became a condition. The U.S. strategy was assured destruction, but the condition between the U.S. and the Soviet Union was mutual assured destruction, or MAD. And that created, when it was popularized, a lot of cynicism in the public that these guys are all nuts. They're trying to, they're thinking all about targeting to kill millions and millions of people. In fact, the targeting was less and less about counter value and mostly counter force, but also counter urban industrial. This would be an example of a Nagasaki attack. Nagasaki was a big industrial base. Now, I didn't get into enough detail about the military themselves. After the Air Force was established in 1947, they set up the main organization to deliver nuclear weapons, the Strategic Air Command, SAC. And the Strategic Air Command is at Offutt Air Force Base in Nebraska. That's where the nuclear targeters live. You could be a 25-year-old Air Force lieutenant, and you're in an underground silo with a computer determining which targets you might want to hit with those missiles. SAC was the key to U.S. nuclear targeting from 1947 to 1994, so after the end of the Cold War. Michael Knopf anecdote. I was in the Arms Control Agency of the Clinton administration in 1994. And because I was working on negotiations with the Russians and the Chinese to a lesser extent about nuclear arms reduction, I had to understand much better how the system works. I was invited out to SAC. But SAC had just changed. SAC was downgraded in its capability. It was given less money. It didn't have the control of all the nuclear weapons. And there was an Air Force general, a US Air Force general, who had supported that, saying the Cold War is over, the nuclear standoff with the Soviets is over, we don't need to have this lethal capability. And his name was Butler. And I went to be briefed by the SAC commander. Butler had already left. And someone said to me, Mr. Knopf, you might be interested in going into our PX. PX is where they sell t-shirts. And I went into the PX, and they had a shirt there that I could buy. And on the front it said, "Who killed SAC?" And on the back it said, "The Butler did it." General Butler was not a popular guy at SAC. But you can have brainy people at RAND thinking about where the targets ought to be, but it's these guys who control the weapons. Okay? And counter-force targeting has been the centerpiece of SAC targeting throughout the nuclear age. Even though the public debate is about city busting and massive casualties and all that, that's not been what the people with responsibility for the weapons have been doing. They've been trying to figure out ways to destroy the Soviet ability to attack the United States. And as far as we know, although we know less about it, this is the same thing in the Soviet Union. The strategic rocket forces have a similar approach. Any questions about civilian control of the weapons, targeting of STRATCOM, Oppenheimer, Teller, and thermonuclear weapons? Of course, we built thousands of thermonuclear weapons. Teller won that debate. About the weapons labs, oh, I didn't mention, the weapons labs are augmented besides Llano, Los Alamos, and Livermore, and the Sandia Engineering Lab. Pantex is where they assemble the weapons. It's in Amarillo, Texas. And Y12, near Oak Ridge, Tennessee, is where nuclear weapons components are manufactured. And there are a few other elements in the nuclear weapons complex. The Nevada test site is where they tested weapons, although there's been no nuclear testing since 1992. So that's what? That's over 25 years ago. We talked about the RAND basis study. So I didn't finish up on this. Kaufman, working with McNamara, became convinced that massive retaliation was stable, but that nuclear weapons in the theater, in regional context, in Europe or Northeast Asia, was not stable. And different terminology that came into play was central deterrence, that's US-Russia deterrence, or extended deterrence. That's where the US is threatening North Korea with a nuclear attack if the North Koreans attack Japan or South Korea. That's extended deterrence. You understand the difference? You do not? No? So, we have a large number of missiles that can attack Russia. They have the same number that can attack the United States. If they're equally invulnerable or vulnerable, that condition of central deterrence is considered stable. Neither side is willing to commit suicide to attack the other side. But supposing you have allies of the US or the Russians who are willing to attack allies of the United States, is that stable? Not clear. So the US needs to extend its deterrence umbrella in a credible way to South Korea or Japan to deter North Korea from attacking them. This, of course, is a fundamental issue with North Korea today. This is what Trump is facing this afternoon. There was another version of this. It's maybe a little less important. I think this is also in the Kaplan book. President Carter and Secretary of Defense Brown had a slight revision of flexible response called the countervailing strategy. And having a strategy to basically emulate whatever they wanted to do, we can do the same thing. Okay, I only have a minute or two. At the same time as all this was going on, nuclear targeting, the deployment of many missiles, and of course, the US and the Soviets, during the peak of the Cold War in 1967, they deployed, between the two of us, 67,000 nuclear weapons. 67,000 nuclear weapons. You might say this is absolutely nuts, but it showed the intensity of the competition between the two sides. But there were efforts at arms control at the same time. Arms control was a concept originally developed at a summer conference in Cambridge, Massachusetts in 1960-61. There was a young assistant professor at Harvard there who contributed to it named Henry Kissinger. Given the National Security Advisor, Secretary of State under Nixon. There was a future Nobel laureate, an economist of eminent nuclear strategist, Tom Schelling. There were some brilliant thinkers at this meeting. They said arms control is any measure that can reduce the likelihood of war, the damage should war occur, or the funds devoted to war. That's the official definition I've just given you of arms control. To reduce the lethality of war, the budget associated with war, the damage associated with war. And they argued that the US and the Soviet Union, while building other weapons, should try to, through negotiations, reduce the weapons. Through negotiation. And that led ultimately to Nixon. Kissinger joined the government. Nixon became president. And the SALT agreements, Strategic Arms Limitation Agreement, SALT I, was signed in 1972. I'll have to give you more about this next time. There's been a whole range of agreements, bilateral agreements between the two sides, US and the Soviets, multilateral agreements like the Nuclear Non-Proliferation Treaty. So, key additional elements besides the whole evolution of the basing and the strategy are arms control and also defenses, which we haven't discussed. And I need to mention, even now in closing, that these weapons carry multiple warheads, not just single warheads. And they can be, they're reentry vehicles that can be targeted independently, MIRVs. Or multiple reentry vehicles. So that if you have a
a reentry vehicle that has 3 weapons, it can hit one target 3 times, or it can hit 3 different targets. There's tremendous leverage in having multiple reentry vehicles. This has become another key element of nuclear strategy. Okay, I've thrown a lot at you today. I hope you got some of it. And do read Kaplan. Now, don't go away a second. So now, today is the 12th. So on Wednesday, the 14th, Professor Bernstein will return. And I think he's going to do more on technical weapons. I may do something on defenses, I don't know. And then a week from today, the university is closed on the 19th. So we'll have to, this is a chance for you guys to catch up on your project. Okay. Thanks very much.
Graded homework 1s are up here.